Today it's my pleasure to be talking about a topic that is dear to me. I spend lots of time throughout my decades of careers working with a variety of different companies on time series analysis. So today I'm going to kind of give you kind of a really brief and general introduction to time series analysis and forecasting, really more from the statistical sense. So if you come from a signal processing or controls background, this will gear more towards the statistical analysis, machine learning analysis, as well as some things from econometrics. So kind of really the goal over the presentation is I broke it up into really these three sections to kind of go over and bring you on board with what is time series, how do we analyze it, and what do we do with that information. Then we're going to give you an introduction to machine learning, kind of a general overview of all the different techniques that are out there, but then also give you a specific example that's really catered more towards time series analysis. And then talk about more really working with more complicated time series, things that are complex, the seasonality to them may be time varying, or there might not be very easy to find patterns with these traditional techniques. And that really falls into how you take advantage of machine learning in combination with feature engineering to build these forecasting models for these complex data sets. So with that, we'll go ahead and get started with kind of a time series foundation. So this is just to get everybody kind of on the same starting point, understanding what a time series is, how do you go about kind of diagnosing it, what kind of models can you apply to it, and building a forecasting model. So of course, we got to start out with the definition of what is a time series. And really, a time series is just a listing of data that's a series. They're ordered in time in the way that they're sampled. Now, the timestamp can have a variety of different meanings depending upon what the time sampling rate is, what the data set it is itself, but really the timestamp can be representations of absolute time, such as shown here. They can be local time, like you could represent these times in different time zones. They could just be dates or days of weeks, or they can be related to the businesses and calendars of different points in time. And then the other one is actually looking at duration. So duration is really, it's related to time, but it's really a time differential. And there's two different durations that you typically see in a time series, which is a time difference. So often when we're sampling data from some kind of environment, it's actually sampled over time. You can start with one timestamp and then it's a unique time difference from that. You can also have different calendar durations, differences between calendar points in time. A lot of this comes around like with financial time series or working with business and day calendar conventions. Those are more differences within specific dates. So they're not uniform necessarily in what you would think of a running timestamp, but they're differentials in days. So these all have different ramifications of how you would include those elements into the analysis of the time series themselves. But pretty much all time series analysis that you apply kind of have one requirement to them, is that the ordering is uniform across time. A lot of the statistical analysis techniques that you apply kind of assume, that they're independent, identically distributed across time. And so this is kind of a requirement that comes out, is that when we work with time series, we want to make sure that the data is ordered uniformly across time. And you'll see more of that as we kind of go through the analysis techniques. But kind of the example I'm going to go with for the first portion, for the first, I guess, 1/3 of this webinar, is really this CO2 data taken from the Mauna Loa Observatory in Hawaii. And you can see the time range data here. There's a link down on the bottom where you can actually get the access to the raw data. This data is sampled daily. It's actually sampled hourly, but this is reported as a daily estimate, so we have daily time points. One of the things you can notice is that this is realistic data pulled directly off the NOAA website. You can see that there's missing data sets here. There's a lot of noise within the zoomed in time set. So this is kind of the characteristics of a real time series. One of the first things we have to do when we start working with it is get it into a form that we can actually use to analyze it. So with this one, there's a variety of different characteristics of why I chose this time series, because one is you can clearly see a trend. There's an upward growing trend over time of how CO2 emissions have been growing over time. There's also a cyclical component or a seasonality to it, which you can see is about averages with the seasons throughout the year. It's about 365 days in length. So it goes between, winter to summer, and you can see how the CO2 emissions change with that. And then other characteristics of time series not necessarily shown by this one are, you can have regime shifts or change points. So if you look at like stock market data as an example, often you'll see kind of a regime shift or jump diffusion processes that happen there, where the prices will be going one way during a bull market, and then they'll shift into a bear market as an example of a regime shift. And an important characteristic is also autocorrelation. So time series, we really look at autocorrelation as a defining characteristic. One of the most naive models you can throw onto a time series set of data is just use the last data point as the prediction of the next data point. And that's really implies that the time series has a relationship to the past and maybe several lags into the past as well. And we'll talk more about autocorrelation in a few slides. But some complications that arise from real time series is that they're non-stationary. We often like to model things, on a stationary sense. So we want to remove the trends. So we've gone through a step of removing the trends from this time series. Other things that cause non-stationarity are irregularities in the time sampling. So if you're not sampling your data set or the observations are not uniformly sampled in time, that can complicate the analysis as well, because many of the analysis assume that there's a uniform time differential between the observations that you have. And then there could be any irregularities in frequency. So if you look in the frequency domain, you can see that there's a cycle here of about 365 days. If that cycle changes and it's no longer 365, it goes to like maybe 252 days and back to 365. That's an example of how frequency changes might cause non-stationarity as well. And then of course, any missing data can cause problems throughout the time series analysis as well. So let's begin kind of modeling this time series. I'll introduce different concepts of statistical modeling approaches you can use as we kind of go through this and explain them. But basically, we're going to go through 5 steps. We're going to try and define a model as represented above before, where we have Y is our observation. We're going to look at what we can define the model as to capture the trends, the seasonality, and anything else we can discover about the time series, and then the noise component. So the first step will really be we need to clean the data set. Then we're going to define training, validation, and test sets so that we can compare how the model prepares in sample versus out of sample. We'll also look at different tests you can do for non-stationarity. We'll then select a set of different models we might apply to this and show the results. And then we'll evaluate the results based upon some common error metrics and some diagnostics plots. So with that, let's go ahead and get started. So here's kind of the picture of the data that we have. And just for context, for those of you that are interested, I'll be able to provide a link to the source code in Python if you wanted to go through this analysis in more detail, as you can. So, but you can see that the data itself is really kind of textual data. There's a whole description to it, and then down below is actually the tab delimited data set. You can import it using a variety of different techniques. Here's what the data looks like when it's imported. When you plot the data and then the missing data that we're going to fill in, you can see that the upper plot is the actual plot of the time series. The orange dots overlay are the filled in missing points that we wanted to do from the prior time series. When you actually zoom in, you can see here that the missing data is not actually that much. When you calculate it out, it's about 15% within this data set. But we do need to fill those in so that when we end up with a time series that we can use within Python and analyze it, that the data has actually been correctly calculated and filled. So in this example, we just did a linear interpolation to fill in the missing data. So we're not going back in time prior to the 1975 start time or forward at all. We're just filling the missing data points in with linear interpolation so that now we have a uniformly sampled data set. An option could be that if you did drop these out, that's often a case that you do is you typically drop missing values out, but in time series analysis, that would cause problems because now you no longer have a unique time sample between this data point and this data point. So when you're working with time, it's important to make sure that you do actually treat missing data and fill it in somehow if you need to. So the next one is actually how do we create supervised learning sets that we can learn from? And there's a variety of different approaches that you can use. You can use it like a train test split, which is very common. So you just split it into kind of 2 different sets, a training and a validation, and then a test split, which allows you to kind of get a performance valuation across how the training and validation and then out of sample performance and tests would do. And then with time series, there's special considerations of how you might apply these train tests or validation splits. You can do them in a way of like a sliding window where they can be moving forward in time. So this is how you can do kind of like 1 step ahead or a windowed-based forecast into the future. And that way you can learn data throughout time as it continues to build the model. Or the expanding window, which now kind of keeps a whole track record of the history and then kind of allows you to build that into your model and then have your test sets out of that. So for the purpose of this example that we're showing, the plot on the bottom actually shows what I've broken it up to as a training and a validation and a test set. Basically, we're going to use the data from 1975 to around 2010 to build the model. We'll then test it on the validation set from 2010 to about 2020, and then we'll actually test, do an out-of-sample test set for 2020 going forward. So now one thing I want to talk about is the next step is to really get into removing stationarity so we can apply different models to it. Now, stationarity defined is really a process that has a constant mean, a constant variance, and also has a constant autocorrelation structure. So those three requirements are what you need to satisfy in order to be able to use a lot of statistical or econometric techniques to model a time series. And then, as I mentioned before, we talked about different examples of non-stationarity, but over on the right is a plot of a variety of different processes. And as you can see, there are two here that actually have trends to them. There's a trend stationary, so this is actually just a linear trend that goes forward in time. There's something that's also called difference stationary. So one of the things you do to often remove stationarity is do differencing to the data set to actually remove the stationary so that you can then analyze it. There's an autoregressive one process, a moving average one process, and then a combination of autoregressive moving average processes, and then a heteroscedastic process. And one thing you can look at is you can look at all these different processes that were generated using these different stationaries, and looking at them, you can see it's kind of very hard to understand whether they're stationary or not. So the trend stationary and difference stationary, these are not stationary signals. The AR and MA and ARIMA are, and the heteroscedastic one is not. So this one is the one that's actually changing the variance over time. And it's called heteroscedastic, and that means just changing variance over time is really what that term means. So if you actually look at these processes zoomed out with a longer sampling time, now you can actually kind of infer and see the trends, right? You can now see that this trend exists here. And there's just a little bit of noise around it. The different stationary looks a little bit more noisy, but you can actually see that it's trending upward. And then the other ones, it's harder to see if there's a trend or not. So this is kind of the challenge with time series analysis, is being able to detect trends and then remove them prior to doing any kind of analysis. And some statistical tests that you can run to do this, there's quite a few that are out there. I'm listing 5 here that you can go through, and I'm showing results for 3. But basically, these tests they're just statistical hypothesis tests that will look at your time series and then give you a hypothesis whether it's stationary or not. Right. One of the most commonly used one is the augmented Dickey-Fuller test. And that test is used to check whether a time series is stationary or not. So the null hypothesis is really that the time series has what is called a unit root, which means that it's non-stationary, against the alternative that it is stationary. And you can see that the hypothesis in the EDF test in this case actually comes back false. So it says, yeah, there's a trend within the CO2 data. The KPSS test is actually slightly different in that this test is testing the null hypothesis that the time series is stationary around a deterministic trend. So it's testing for a deterministic trend and that it's stationary when you remove that trend. And this one's saying that this is true, there is a deterministic trend. And then it also kind of gives you an indication that there is a trend here as well as one of the outputs. And then there's a Phillips-Perron test that is similar to the ADF test, but it's looking for serial correlation in the errors. And it kind of gives you an estimate of some of the serial correlations you can put in. But this is an example of using a statistical test to kind of understand whether there's stationarity to your signal or not. But there's a variety of other ways to do it, and the visual ones are often the most useful for looking at your data and diagnosing it and understanding the types of stationarity you might have, right? So we showed this original line plot before. Other ways of looking at it is also looking at scatter plots. You can clearly see the trend, both the linear trend going upward, as well as the seasonality oscillating about the trend. Other things you can do to test for stationarity is, if you recall, the definition of a stationary process was that it has constant mean, constant variance, and constant autocorrelation structure, right? So if you just split the time series into 2 halves and plot their distribution, if they don't overlap, the series is non-stationary. So you can see that as a result in this histogram shown over on the right. Another way to look at it is a box and whisker plot, which kind of gives you the same view of a histogram, but the box basically represents the distribution in terms of the quantiles. And you can see how that's changing over time. And the nice thing about the box and whisker plots is you can also see that it typically reports things that might be an outlier. So there might be outlier points within this data set that might actually be sensor error or things that just didn't fit the normal pattern. And then the last one, which I'm going to spend a lot more time on in the next few slides, is really looking at the sample autocorrelation plots. There's 2 of them. There's the autocorrelation function and the partial autocorrelation function. So what the autocorrelation function does is this plots the correlation of the time series with itself and lagged values of it. So you can see that in this particular example for the CO2 data, that it's correlated across many lag samples. This is really an indication in the ACF plot that there's a trend within the data set. And then when you look at the partial autocorrelation, what this is doing is actually removing correlations at different time periods and really just looking kind of at the error terms. And you can see that there does tend to be a correlation with one time point and then it drops off. In a few slides, I'll kind of give you some guidance on how you can interpret the correlation plots in terms of estimating model orders and different model parameters. But this is a useful diagnostic plot that can really tell you a lot about your time series, even before you start modeling, as well as when you apply it to the residuals after you build a model. So when we look at reading the ACF and PACF plots, there's kind of 3 different models you can think of when you read those plots themselves. So the first one is once you remove the trend, once you plot the residuals after the trend is removed, you can see different types of characteristics. And this first one is how do you diagnose for an autoregressive model, which is basically taking the time value of what you're trying to predict with a lag value of itself with a noise term. And then the autocorrelation or the autoregression of order P is basically just how many terms and lags you have incorporated in there. So when you're looking at an AR1 process as plotted here, you can see that the AR1 looks like this. The actual autocorrelation function has a slow decay over time, and then the partial autocorrelation function has a steep, sharp drop-off after the order of the autoregressive characteristic. So you can see that it tails off gradually and cuts off after P. So if you have a ACF plot that looks like this, that's an indication they have an autoregressive process, and we can model it using something like this. The other one would be a moving average process, which now takes the observed values, and we're now modeling against lag values of the noise that you have over time. So when you look at the parallelogram plots based upon trying to diagnose a moving average, what you have here is this one showing a moving average 1 process. You can see that the ACF plot basically has a sharp drop off after the number of terms that might be there. And then the PACF has kind of a slowly decaying. So this one had a slow decay and a sharp drop off here. This one's the inverse, a sharp drop off and then a slow decay, and that tells you that there's a moving average process. So if they look like this, it's an AR process. If it looks like this, it's a moving average process that you can model. And then there's a combination of an autoregressive moving average, which now when you're interpreting the ACF plots is a little bit more challenging to figure it out. But you can see that there's also tends to be a process that's slowly decaying over time on both of them. Typically, you can look at this and say, well, there's a slowly tailing off gradually here and here, so this might be an AR1 type process. That's what we have here. So you can start with that. It might be an AR2 or an MA2, depending upon how it's actually constructed. But this is how you can then start to select orders based upon what these plots are telling you to add to your time series modeling. So when we look at the types of models that you can apply to predict time series models, there's basically a variety of different ones, but I'm going to cover conditional variance models in some of the examples we'll show. There's also conditional mean models in the examples I'll show for the CO2 data. There are also conditional variance models that work well for things like stock market data. And then we'll talk about other models that are out there as well, but not dive into them too deep today. But basically what we have is you can look at the autoregressive, which we talked about before. I'm introducing the lag operator representation because this makes it actually even a lot more convenient to represent some of these models in shorter form. But basically the lag operator is just an operation on the value of interest with a time function, right? So you apply the lag to y of t, that would be t minus 1 all the way to order p, right? And then similarly for the moving averages, and then I mentioned the ARMA on the previous slide, but there's also an extension to that called a REMA. And what we do with the REMA is we're actually introducing that difference operator. So now you can add a difference operator into the mix, which will difference the data set. Then you can apply AR and MA models on top of that, and that's what this one looks like. So we're really just kind of introducing the ability to difference y of t. So we're taking a number of orders. Typically, you don't need to go more than 1 or 2. But this will just give you a representation for some differencing operator up to D. And then there is extensions to this which apply seasonal ARIMA. And when you think of seasonal ARIMA, it's really kind of taking 2 ARIMA models together with a seasonal component. So there's a seasonal component, a difference for the seasonal, and then the original kind of ARIMA as well. And I'll be showing you kind of I'll be showing you how to apply a SARIMA model to the CO2 data to capture that seasonality. So these are kind of extensions to the traditional ARIMA processes to capture seasonality. And then some things I'm not going to really get into in terms of modeling today, but just for your awareness that there are also conditional variance models, right? So when we think of stationarity and properties we said for modeling, there is the ones about the conditional mean. We can then look at conditional variance, which are now really about the variance. And these work a lot better typically for things like processes that have heteroscedastic variance, like the stock market as an example, that has time varying volatility to it. So anything that has a time varying volatility to it was actually a good model for these models. And these tend to be classified as generalized autoregressive conditional on heteroscedastic behavior, GARCH models. And then there's extensions to the GARCH model called eGARCH, as well as the GJR. So all of these you can see are kind of extensions on, rather than modeling directly the error term or the observation itself, we're now looking at the error term expressed in terms of the standard deviation, and then modeling the squared value of the standard deviation, like we did with the AR and MA processes. So you can put lags on different terms here. And this is what a GARCH PQ model is and an eGARCH. So that just gives you a feel for the different models that are out there. But let's actually apply this to the CO2 data and see how that works. So the first thing you wanted to do is actually, plot the original time series, overlay the PACF and ACF plots. As you can see, when you take the raw data and put it in, what you get is that trend of autocorrelation constant through time, or slowly decaying. That's an indication of a trend. So then you want to remove the trend. The next thing you can do is try to apply a difference operator. So we're doing that through the SARIMA model, just with one difference operator. So this is the time series, this time series, just difference. So taking the difference over time and plotting it. When you run that back through, now I have something much more clean that I can start to think about in terms of building a model around it, right? So as we mentioned before, when I have a sharp drop-off or a long decay, it's the difference between an AR and an MA process. So both of these have kind of a sharp drop-off, but there's a slow decay on both of them. So this is indicating that I have an ARIMA type process, and probably like an ARIMA 1.1, maybe ARIMA 1.2, or a 2 model. So what we do is we actually go through and we apply a seasonal order of the difference, an AR process of 1, an MA process of 1, and then we're also having that for the seasonal operator with 365 days to account for the seasonal variation you saw. And then when you fit this model, you get the results you see in the chart here. So the residuals are plotted on the top, and then in the middle are the ACF and PACF functions. And as you can see, these ones have the spike at 1, which you'd expect to be correlated with itself, and then they're pretty much no other trends there. So this tells you that the model is actually pretty good in terms of being able to capture all the dynamics. This happening with this model. So a SARIMA, a seasonal AR ARIMA model, when applied, actually gives you a prediction that looks like this. So we have the out of sample data. The red is the actual in-sample we use for part of the training. Yellow is the first validation set, and then the purple here is the actual out of sample test with the error term shown here in terms of root mean squared error, and then the mean squared error as well. And then the actual resulting model with the constant and then the coefficient values in there as well. So one thing you can see is that a SARIMA model does a really good job of predicting this future values and then modeling the dynamics of this. And that's one of the great things about SARIMA models or ARIMA models in generally is that they're actually pretty good at modeling time series like this that have fairly uniform characteristics, seasonalities, noise characteristics that are uniform, and so on. Later on, towards the last part of the webinar, I'll talk about what happens when you have some real-time series that are much more complicated with much more human behavior involved that complicate this. But this shows you how you can model fairly sophisticated time series using ARIMA processes. And then the last step is, looking at our goodness of fit. So just because we reported the root mean squared errors, we also want to look at the residuals. So the last thing is actually running it back through a diagnostic check. So if you take so in this other plot, we looked at the residuals here, and then we looked at the resulting parallelograms, and we can see that the model looks pretty good. Maybe there's nothing else to add to it, right? Well, if we square the residual, this is how you can test for the variance changing over time. So when you square the residual and then plot it, you can now see that this shows that there's probably maybe a small process that you could model with GARCH. because there's a little bit of a spike up here, but probably not much worth it. So this model is actually pretty good. I'd say that's as far as we need to go in terms of being able to build a good predictive model here. The other thing you want to do is look at kind of the distributions of the residuals using a probability plot or a QQ plot. The closer it is to the straight line, the better it is. You can see that there are some characteristics to it that are not actually adequately captured by this model, but it does a pretty good job overall. So that's kind of how you can apply traditional econometric time series modeling to like the CO2 data from Model O as an example. One of the other things I wanted to talk about though is like if you look at this model, the ARIMA processes, you get these terms that mean AR, MA, but they don't tell you a lot about the cyclical nature of the time series, and they're harder to really kind of understand. They're very good at forecasting, but they're kind of hard to understand from what's driving the processes, as well as also being able to understand, is there other data I can bring into this, or are there other things I can identify? So I wanted to also introduce you to some automated methods for doing this. There's a package in Python called PMD ARIMA that does auto ARIMA. So it'll do that process for identifying all those lag orders and everything automatically. If it's a variety of different ones, it returns the best one based upon the AIC criteria. And then there's another package from Facebook called Profit, which actually is what I'm going to show on this slide. And how Profit works is it actually tries to fit deterministic curves to your data and then give you the results, but they can be time varying curves. And it tries to break it out in terms of a trend component, the seasonality, cycle component, and then an error term. And you can see here's an example of fitting the CO2 data with Profit. And because Profit has a nice characteristics and it's building a curve, you can actually do backcasting as well as doing a forecast forward. And you can see how well it models the data here and then what the forecast is. The other nice thing about it is it actually gives you detailed information of the trend, the seasonality that you see both in a yearly and a weekly. So behind the scenes, what Profit is doing is some feature engineering. It's breaking up the data set, looking at different combinations of weeklies versus yearly versus other things to help build the model. And something that's interesting you can see is that there's definitely kind of a unique characteristics that happens on Monday and Sunday, which might be something you can expose into your variable. Maybe there's traffic concerns, maybe there's just the way that the business days versus weekends impact the CO2 that is being emitted. So this gives you a little more information. Now you can pull out these same type of charts using filters, which will give you trends and seasonality components. There's a variety of different methods to do that as well. But the nice thing here is you now have a model that's easier to look at and break out the different things, and you can look at things that are driving the underlying characteristics better. So that's an example of using different econometric and even Profit model applied to it. Now, one thing I wanted to kind of leave you with is that just because Profit looks good, you get some good results. The question is how good is this model and can it still be improved? So the nice thing about the ARIMA modeling process we talked before is that they can be used with traditional modeling. It's often called ARIMA X or ARIMA with exogenous terms. So you can build a traditional regression type model and then add on the ARIMA or even the GARCH components to improve that model. And if you look at the Profit residuals for the prediction as shown here, you can still see that there's a process that we can even capture to make it better, right? There's a slowly decaying trend, and then there's a sharp cutoff here. So what this tells me is that there's probably, since there's a sharp cutoff on this one, there's probably an AR1 process that we can also include into this model to help improve it and make it even a better prediction model. So, that's one of the things I always like to do when we're looking at time series is look at the autocorrelation plots, because that tells you a lot about, is there more that I can create? Is there information that's still within the time series that I haven't captured in my model? And then you can take Profit combined with the AR1 model and actually reduce this and get a better prediction. But I'll leave that as an exercise for you guys to look at. So just to kind of wrap up the foundation traditional time series models, we were looking at a univariate time series, and what that means is it's one output to its input. If you have multivariate models, you have multiple outputs that might be correlated in time. So things that you can look at would be like interest rates. You look at the yield curve with interest rates over time, or maybe like interest rates or foreign exchange rates between the Canada and US. Those time series tend to have relationships to each other, and you might want to use a multivariate model to model those different components. Now, the different models that are typically applied is called vector autoregressive models. So they're basically autoregressive applied to a multidimensional vector error correcting models, that's the VEC ones, and then there's Bayesian versions of the vector autoregression models. So those are often used. We didn't look at a time series that actually has change points in them, but if you're looking at regime shifting models that do have that, there are different techniques between Markov chains, there's these Markov switching models, and discrete time switching models that can be applied. So those are often useful for those types of time series when you see that. And then structural and state space models can be used as well. Now, the one thing about this, the SARIMA model that was implemented here, this is actually implemented through a state space approach in the Python library. So I'm not going to dive into a state space model, but they're very useful for modeling time series and discovering a variety of hidden latent variables that you can extract from them. So that's something you might want to dive into deeper if you have time. Now, what I want to do is kind of switch gears a little bit and talk about the more modern applications of time series analysis. Now, one of the things to keep in mind is that you can throw a lot of machine learning models at time series and they do a pretty decent job in many cases, but often they still have a hard time competing with the SARIMA model I showed earlier. So the SARIMA model is a very strong model in terms of being able to build a model that has good predictive performance, and it should be used as kind of your challenger model for anything you use in terms of the machine learning world. But to give you kind of a feel of the different approaches, here's just kind of a matrix of all the different things you can use machine learning for. You know, there's different types of classes of machine learning problems. There's unsupervised learning, so that's where I apply a machine learning model to the data to just learn what the data can tell me. Often those are used for dimensionality reduction, reducing the number of components in your data that you need to do to capture the characteristics, or clustering. And then there's the ones that we're really going to talk about here, which are really classified as supervised learning. And what supervised learning is I have a training set, I learn from that, and then I apply it to an out-of-sample data set. So I'm allowed to learn based upon an input-output characteristics for the supervised learning. And then I also have listed the reinforcement learning because it's a big component of the machine learning space these days as well, where reinforcement learning is largely used more for prediction. So two things that I'll probably show later on is I'm going to show an example of a decision tree towards the end of this, and then we'll also look at deep neural networks because this is a big topic. And one of the things you notice is that decision tree models can span a variety of different applications from clustering, classification to regression prediction. And then one of the reasons deep neural networks are exciting and to talk about in the machine learning space these days is because they have a wide use of applicability across the whole spectrum, right? You can use it for a variety of different problems. Now, when we talk about what is a neural network, well, schematically shown on the left here is a picture of what a neural network is. So it's really just taking a variety of inputs, running them through weights, and then combining them somehow. This one's using a summation operator. And then there's usually some kind of activation function that will activate how much this particular operation is important or not. So that's the basis of really a shallow neural network. And when you want to build out a more complicated neural network, you just kind of wire these things together in a deeper and deeper fashion. So here's an example of a neural network that has 7 inputs, 2 hidden layers, and then it's actually doing a multivariate prediction with 2 outputs. So you can wire these all together, and that's kind of the unique characteristic of a neural network is that you can build very complicated models very quickly, and then be able to identify patterns and do predictions quite well. Now, the challenges with neural networks is that there's a variety of different architectures for different problems. So depending upon what you're doing, from image processing to time series like we're looking at here, there are a variety of different structures that work well for those and that don't. And that's part of the art of applying neural networks, especially in the deep learning space, is choosing the right architecture for these models. So I'm going to talk about one of the most common ones that's used for time series, and this was an extension that was done off of the original neural networks to be able to handle kind of the characteristics of a sequence data that has a long and a short-term memory component. And that's really where the long and short-term memory networks come into play. So schematically, the graph is shown here. Is what I have is I have the inputs that come in, and then there's a cell output and a hidden output that go to the next network if you connect them into series. So that you could think of them, this is many of them connected together like this. But you have basically a forget gate. So this gate is taking the inputs, anything from the hidden layer from a prior node, if there is any, and it's telling you how much I want to remember or forget about that particular characteristics, and it goes into the cell here. Then you also have 2 other gates here that are really geared towards kind of identifying how much of the inputs am I going to weight, and then also be able to promote to the cell. And then the last one is it's going to weight the outputs with a combination of some kind of activation function that will then give you the hidden state, right? So now I have the output and the hidden state that continues to go through this process. So you can wire these LSTM networks together to build fairly sophisticated models that have good characteristics for time, and that they're able to kind of learn different long and short-term characteristics of the data. And then, for those of you who are mathematically inclined, here's the expressions for each of those different components. But really all it is, it's a weighting of the inputs with some other weighting of the hidden elements sequenced together. So if we build an LSTM model for, say, the Apple stock price, I ran this morning, so this should be updated as of this morning. But basically what you can do is you just wire together a variety of different layers. So this is back to the architecture of how you do that. So in this case, we're going to create a sequential architecture. So that just means everything goes through sequentially. There's no other parallel paths within the network. We're going to add 2 LSTM networks of size 100, and then some dense layers to combine the output into one final output, and then run the model. And then this is the resulting structure of the LSTM network that we've created with 2 layers, and then the outputting results. And you can see how well it's predicted Apple's price over time. And then more recently, so what we did is the training set was we trained up to about 2015, and then the testing set was 2015 forward. And you can see how well it's been able to predict. It did a pretty good job to begin with, but then later it kind of started to drift and under-predict the Apple time series. Now, one of the things you don't often see when you see people modeling time series with machine learning approaches is to actually take the residuals from that modeling process and throw it back into the ACF and PCF plot, like I've talked about before. So when we do that, we see the residuals here for the forecast. You can see that for one thing, they're all below 0, so it's under predicting, and then there's a slight downward trend to the residuals as well. So it's gradually getting worse and worse over time. So that's an indication that this model isn't good for long-term forecasts, but maybe we should use it just for shorter-term forecasts, maybe a year, a month. That's something to look into. The other thing to look at is that you can clearly see that there are trends. So this model as well could actually be augmented by an ARIMA-type process. Probably, again, another ARIMA 1, maybe ARIMA, or an autoregressive 1, autoregressive 2 type of model would capture a lot of this characteristics and help. So, that's a good way to say that, even though that this model might look good, or even like the profit one look good, there's still more we can learn from the residuals to help improve the model and get better accuracy using traditional econometrics approaches. Now that kind of gives you an overview of how to apply machine learning. I want to actually show an example using a decision tree for regression, but also talk more about temporal feature engineering. So one of the things that I mentioned before with Profit is Profit did a lot of things to extract like day of week, month of year kinds of things. So it did some automated feature engineering on the back end. But when you think about feature engineering in general, if I wanted to do that in my own process and take that CO2 time series data, or even the Apple time series data, add in features that are lagged in time, maybe look at dates in terms of days of weeks, Monday, Tuesday, Wednesday versus Friday, things like that, temporal feature engineering can be very messy. And one of the requirements is that, it has to be time series. You can have temporal transactions which may not be uniform in time. So that now starts to complicate the requirements I mentioned before about having frequencies that are uniform, or having time sampling that's uniform. So how would you take transaction type data and then sample that into a uniform time series as an example? That complicates the process, as well as different discrete events that occur. Maybe you have a sales process where you're having a markdown on a certain day like Black Friday. Now these things complicate the traditional time series approaches I showed you and make it much more harder to model. And that's where actually machine learning combined with the temporal feature engineering can actually bring a lot of value, because one thing machine learning is really good at is pattern recognition, right? So when you use machine learning techniques, you don't necessarily have to have everything sampled as uniformly in time, or have characteristics that are influencing the data set, features that are influencing the data set that are uniform. So now you can introduce more non-uniformity into this and build more sophisticated models that have better prediction capability. So the whole goal is, how do I take this type of information, generate a feature set of tables that I can then run through traditional machine learning type of algorithms, right? One of the things that we do at dotData is we actually create a feature factory that makes it easy for you to do this. And that's one of the things I'm going to talk about in this next section of the webinar, is how we do that. And really what we do is we you take your inputs, you just define the relationships, whether they're from multiple tables or a single table, and then you can define a variety of different aggregation and filters that can happen. So you can have aggregations across time, you can have events, and a variety of other things that's shown on the listing below the table. But to kind of give you an example of what that looks like, you can generate a feature that has a variety of different characteristics. One here is that you can see aggregation of lag values. We mentioned before in the autocorrelation plots that lagging is typically very important for time series analysis. You can have things that are just time intervals. You can have categorical values such as date, which may, Monday, Tuesday, Wednesday is kind of a categorical value as well. You can have different holidays that are important. And then you can have combinations of these things that need to be applied in terms of generating good features. So to give you an example of how that works, we took a model of profit on a Walmart data set from a capital competition from I think 7 years ago, and ran that through dotData as well. And you can see one of the things, profit was really good, and it returns a lot for models that tend to have good cyclical seasonality or good patterns over time that it can pick up on. This particular model, you can see that during the training set, the validation set, and the test set, it didn't do very good in terms of being able to predict it. You can see the red line wasn't really capturing the non-uniform characteristics over time. When you run that through Feature Factory with a light GBM decision tree, which is a different type of model compared to this one. This is more like curve fitting, and this is more like using a decision tree to model it. You can see a very good representation of the resulting capabilities of the sales forecasting for one store. So when we look at what that was, the features from profit are kind of over on the left. You can see that it does a good job of extracting yearly, weekly, daily seasonalities, linear trends, or even nonlinear trends in some cases. And then you can add things to it, but it's hard to add anything else to it. So if I actually wanted to add a REMA model, you can add it in as an added model, but you'd have to build it outside. The other thing is, if you look at the features that dotData does, it does similar features in terms of time, but it also does a variety of other ones. You can include max and min and standard deviations. There are other mathematical features like a continuous wavelet transform. As an example, it looks at other things like recency, and then it also has some feature awareness such as hierarchy. And this is all completely customizable and automatable that you can use through the dotData Pi library. But it also handles US holidays automatically. So you get features that can actually be more helpful in describing your model that can be then put into your machine learning models. And so that's really kind of the summary I wanted to do today, because we're really about out of time in terms of the time frame I had for this webinar. But I showed you kind of the dotData Feature Factory, and one of the things that we're offering is an early access to the latest release. And there's a link here on the left that you can go to sign up for that today if you wanted to see it in action. One of the things we're doing is, since this is an early release, we really want to get feedback on how these features, if you're using them in your process, are useful for you, generated from dotData. And we're giving Amazon gift cards with up to $100 for valuable feedback we get. So if you're interested, please go to the link there, and then we'll get you access. So that's kind of the summary of my webinar I have for today. I guess at this point we can open it up for questions.